Interested now in looking at trying to find what are called double integrals. And so instead of looking at the area underneath the curve, we want to look at the volume under a surface. But do you see the similarities in it? Okay, so we're going to try it using Riemann sums. So here is a surface. No, there is no surface there. There is a surface right here, and I'm trying to find the volume underneath it, right? So what I do is I cut up a bunch of rectangular boxes, and I try and find the volume of each of these boxes. And if I could find a formula for the volume of each of those boxes, I would just add them up, wouldn't I? If I add them all up, I'd get an approximate volume. Do y'all see the connection here? Now, if I do more little boxes, right? Smaller and smaller little rectangular boxes in there, I'm going to start to get closer and closer to the true volume, right? And the way to actually get the true volume would be to let the number of those go to infinity. But that means turning a sum into an integral, right? So let's try and see if we can come up with a formula that would give us a volume of each of like an individual box. And this is my best rendition of it. First of all, since we're looking at the ground, right? This is a three-dimensional drawing. Here's the ground. Our ground is going to be a rectangle. All right? And we're just going to look above that rectangle up into the surface. So this is us looking straight down on that rectangle. If I pick some little dx, remember dx came off the x-axis? Some little dx, and I pick some little dy this way, I create this little box right here. If I pick some point inside that box, it would have both an x and a y coordinate. I'm going to call it x sub I, y sub I, and I plug that into the surface, it will pop up and it will be some value, and that will give me a height, won't it? And the volume of this is what? Length times width times height, right? So isn't it, this is the height, this is the width, and the height. I mean, sorry, length and width, right? So that's the volume of one of those little guys, and I want to add it up forever. But the thing is, you have to do a double summation. And the reason you have to do a double sum is, let's say you fix your dx this way, and then you start moving this way. So you take a sum in this direction. But you also have to take a sum in this direction. You have to move your x's over back and forth and your y's back and forth. So it becomes a double summation. Right? It's the limit as you let the number of these rectangular boxes go to infinity of a double sum, which creates a double integral. And then this right here is this formula converted over. Do you all see that? And that's it. That's how you find the volume. It's our formula. It's what we're going to use for the rest of this section. Okay, so if you're trying to find the volume between some surface, f of xy, and the xy plane, which would be the ground, over some rectangular region. Now notice the way that we write the rectangular region. We write the closed interval AB cross CD. It's not a cross product, okay? That's just the way we write a rectangular region in R2. Then it's given by this double integral. Pay attention to this. Double integral over R. R is what? R is the rectangle, right? The double integral over R of f of xy. This right here represented what part of the picture? The f of xy was the height, right? So this was the height of it. This right here, D capital A. What do you think the capital A stands for? Area, right? It's an infinitesimal area on the ground. If I go back to that picture, this right here, that yellow piece right there is delta x times delta y. That's a little area on the ground, isn't it? So that is actually the dA. And now if I just change that over, this is what dA is, right? dx times dy. Or it's this other formula. What's the difference between these two? Let's see. This one, let's look at this one. If we work from the inside out, the inner integral, which I mean right here, the limits of integration are c and d, aren't they? C and d are your y values, aren't they? And I'm integrating with respect to y. Then I have an outer integral, which takes this answer and integrates from a to b and with respect to x. And that's because x is, corresponds to the AB, right, the x-axis. I could, though, do it the other way around. I could change the order. I could go from a to b, do it with respect to x first, take that answer, go from c to d, and do it with respect to y. All right? Both of those are at your disposal to use. You get to pick which one. If you're integrating over a rectangle, and only if you're integrating over a rectangle. In the next section, we integrate over more complicated regions, and you can't just switch it up whenever you want. So the rectangular region to integrate over is the easiest out of all the regions we're going to integrate on. So how do we integrate something like I just said? How would we do this integral on the inside? According to what I'm saying here in the notes, if you're going to take the antiderivative of a function of two variables with respect to y, you're going to treat x as a constant when you do your antiderivative. Just like when we did with partial derivatives, we're doing basically like a partial antiderivative now. We're going to hold one constant and go backwards. So the inner integral is this one in here. Since it's with respect to y, we hold x constant. And then on the outer integral, once we get to the outer one, x will be your variable. This one, it's the other way around, right? We're going to integrate with respect to x first, then we're going to hold y as a constant. Once we've done that, then we integrate with respect to y. You just got to see these in action. I think it's time for an example. I had this problem earlier. Let's do the problem first, and then we'll take a look at it. Find the volume under this thing on that rectangular region. So I'm going to draw a quick picture of the domain. My domain, what I'm integrating over, goes from 0 to 2 and 0 to 2. 0 to 2 on my x and y, right, or my x-axis, and then 0 to 2 on my y-axis. So this is A, this is B, this is C, this is D. So it's actually a box, isn't it? That's my region. I'm going to call this R for a rectangular region or a rectangle. So to do this correctly, I'm going to do a double integral over R of f of x, y, d, a. Okay, now it's my choice on which I want to integrate with respect to first. So I'm going to write double integral. Let's go ahead and write the function in here. 16 minus x squared minus y squared, 2y squared, oops. Would you like to integrate with respect to x or y first? You want to do x? Okay. Let's do x. And then we'll do y after that. So what I'd like to do is break this up. Everyone understand we have an inner integral, that's the one in red. Then we have an outer integral, which will be the one with respect to y. Now, we're going to do triple integrals in this class too, where we're going to have like an inner and then like a middle and then an outer. Right now we're just at a double integral, so when I say inner, I'm talking about the one on the inside, right? So let's take the antiderivative. Let's go ahead. Oh, wait, we forgot our limits of integration. What's the limits on here? 0. We can't get it wrong because they're both 0, 2, right? But it's the x's, right? I'm pulling the x's, so I'm pulling these two. And then this one is also 0, 2, but that's the outer one because those goes with the y, right? All right, what is the antiderivative of this? And I'm going to leave this integral out here. I'm going to do my work on the inside. Let's see, dy over here. What is the antiderivative of 16 with respect to x? 16x, right? 16x. What is the antiderivative of negative x squared with respect to x? 1/3 x cubed. Everything seems pretty normal, right, so far? That's what we would expect from Cal 2. What's the antiderivative of negative 2y squared? Negative 2xy squared, or you could say y squared x. It doesn't matter. I'll go in alphabetical order. That okay? Now, the reason why, everyone understand, if you were to take derivative of this with respect to x, you treat the negative 2y like a constant, then derivative of x is 1. So this would turn into negative 2y, which is here. So when you're going backwards from y, x is popping in here. That's all that's happening. Understand that? Okay, that's the antiderivative. But we want to evaluate this where and where? 0, 2. Now we need to be a little more specific. What is it that I'm going to be replacing with 0 and 2? The x or the y? The x. So we're going to start writing down x is 0 and x is 2. And that's because we don't want to confuse ourselves, especially when we get to triple integrals. We're going to have x, y, and z, and you got to keep track of which one you're plugging back in for. So the way I did it in Cal 2 is I took this number, I plugged it in. I subtract from that what I get when I plug in this number, right? So let's go ahead and do that. So this should be equal to, I still have an outer integral I have not touched. Okay, let's do this. Plug in 2 for x, and we get 32, right? Take away, what, 8/3? And then plug 2 in here for x, right? Minus 4y squared. We good? Now, now plug in 0 for x. Nice. Everything's gone, right? Any questions? This is a lot cleaner than Lagrange multipliers. It's more straightforward than all that. All right. I think I can get rid of the red brackets. I think I can just go to my integral. It's the integral from 0 to 2. Maybe get a common denominator there. What is that? 396 thirds minus 8/3, right? 88/3. That fair? Now you're just integrating with respect to y. So now, I mean, this truly is like a Cal 2 integral, except y instead of x, right? So antiderivative of this is 88/3 y minus 4/3 y cubed, evaluated at those 2 points. So yeah, this is y equals. Yeah, I'll put it in here because we're at the last variable anyway. But yeah, let's keep reminding me to do that because I forget all the time to do it. Plug in 2. What do we get? 176 thirds. Is that right? 176 thirds minus 8. 32 thirds. is 144 thirds. That goes in, doesn't it? 48? Hold on. Yeah, 48. 48. That's the volume. It's a unitless volume because we don't know what any of this is measured in. All right, should we take a look at the picture? Just to get an idea. Any questions on it? Okay, so geometrically, here's what's happening. Here's the domain, right, that lives on the ground, right? That's our 0, 2, 0, 2. Here's the actual surface itself, okay? There's the surface. I just graphed some of it. That's not the whole thing. If we just take the edges of this and plug it in, this will give you some idea of where it's going to map to. So, man, this is all messed up. Can you all see that on top of that surface? So just those points getting plugged in, and then I'm going to take all this crap out of here. There's the thing we're looking at. Underneath that surface, straight down on top of that rectangle, take all this junk out of here. What is the volume of that shape right there? 48. Cubic whatever. Okay? That's what it is. It's kind of cool, huh? Now, we went with respect to x first, didn't we? What would have happened if we went with respect to y first? We should get the same answer. All right? I won't do it, but you can check for yourself. How about this one? This is really almost the same exact sort of setup, isn't it? I'm going to draw the domain over here. This time it's not 0, 2, 0, 2, so it's a little more complicated. X and y. X is between 1 and 2, so that's 1, here's 2. And the y value is between 0 and pi. That's r, right? So I want the double integral of the function of x and y with respect to area. So I'm double integrating over r. Okay, it's your call now. Let's replace that function in there. And now let's discuss this. I have options, don't I? You want to integrate with respect to y or with respect to x? We didn't do y last time. We did x last time, right? You want to do y this time? Why don't you want to do y this time?
Because with x you can pull y out.
Yeah, look at this. Hold on. I mean, this time, it actually is worth it for us to think through what the integration is going to be. So let's talk about both possibilities. First, let's talk about if we were to do it this way. All right? Focus all your attention on this right here. Right there, which variable is going to be a constant in the red brackets? Which variable is a constant? X, okay? So x may as well be the number 1, right? It's a constant. Let's just act like it. If x was 1, then you had to integrate that right there. How would you integrate that? Integration by parts. That's what it would take. right? This would take integration by parts to do. What was the number? It was, I mean, sorry, what was it? It was x in there. So do you feel like doing integration by parts? Sure we do. But would it be easier the other way, right? Would this be easier to do it this way? Now you're treating y like a constant, and so who cares? That may as well not be there. The antiderivative of sine of xy, again, y is a constant. Antiderivative of sine x, I'd rather do that than integration by parts. How about you? So there is where we actually need to consider whether or not the integrand is easier one way or the other. So this is preferred.